Okay, so hi everyone. My name is Thiago Holleben. I'm a PhD student, fourth year in Canada, Dalhousie University, and I work with Sarah Faridi. So my interests are broadly in the interactions of commutative algebra and combinatorics. And I would say that there's like two types of questions that I'm usually interested in. So the first type of question is, given a property that you like in commutative algebra, should you expect this property or should you not expect this property? Like for the class of rings that you study, is it common or is it not common for this property to hold? And the other type of question is, how bad can the behavior be when, let's say, the property doesn't hold? So for example, take your favorite invariant. What is the largest value that this invariant can have? Okay. So in terms of studying average behavior, what I have done, and for me, it's usually about square free monomial ideals, because I'm interested in combinatorics. But one of the things that I have done in terms of studying average behavior is you have this property called the weak-Lefschetz property. And the idea is for rings, you have the notion of regular elements. And if you go to Artinian rings, you could define a notion of regular elements that still makes sense so that you could have one. And that gives rise to the definition of the weak-Lefschetz property. And then the idea is, if you look at specific square-free monomial ideals and you look at some probabilistic model, should you expect the weak-Lefschetz property or should you not expect the weak-Lefschetz property? And one of my results is that in a specific setting, you should not expect the weak-Lefschetz property. This was a little bit surprising because people usually tend to expect the weak-Lefschetz property, but that's, I guess, one of my results in that direction. In the other direction, in terms of studying extreme behaviors of invariants, I have an ongoing project with a group of 5 people. And what we're looking at is basically you pick an invariant in commutative algebra that you like. It could come from symbolic powers. It could come from integral closures, Betti numbers, associated primes, whatever you want. And the idea is, how high can this invariant be? And it turns out that if you fix the number of generators that you have for your square free monomial ideal, what we were able to show is that as long as, let's say, we have a list of invariants, but the idea is that if your invariant does not depend on the degree of your generators, then there should be one ideal, and it is the same ideal for all invariants, that maximizes all of these invariants. So it maximizes Betti numbers of powers, things coming from symbolic powers like resurgence, asymptotic resurgence, as long as you restrict to square free monomial ideals on a fixed number of generators.